Okay, so today we're going to talk about section 3.1 in the text. This is about maximum and minimum values. So this is section 3.1. So in order to discuss this, I'm just going to draw a picture of just an arbitrary graph. Here's the graph of y equals some function of x. And so when we talk about maximum and minimum values, maximum and minimum values are positions on the graph that are either globally or locally higher or lower than any other point on the graph. So if we take a look at these two values right here, let's give them names. Let's call them, we'll just say A and we'll say B here. So this point right here and this point right here, take a look. This point on the graph is a little bit higher up than all of the points that are nearby to it. So this value right here is what we might call a local maximum for the function f, or local maximum value, and so, or we might say that f has a local max at x equals a. Okay, we might say that, and the reason for that is because if we look at all of the values nearby to a on the x-axis, all of those get sent to points that are lower than that height value on the graph. The same thing here. We notice that all of the points on this graph nearby to B are sent to heights that are higher. So we might refer to this as a local minimum value. Okay. So that is we might say f has a local minimum at x equals b. So f has a local min at x equals b. Okay. And what about more globally? You'll notice that what we've indicated here is that there doesn't appear to be any highest point on the graph of this function. Here the function is just going to climb, looks like without bound, and here it's going to go downwards in height without any sort of bound. And so it doesn't make sense for us to talk about a smallest or largest maximum or minimum, just what's happening nearby. So this is the definition of local. But let's draw a couple of other graphs. Okay, so here's a graph, something easy, x squared. We like x squared. Okay, here, this point when x is equal to 0, this function has an absolute lowest point on it. So we would say that this value right here, f has an absolute minimum value at x equals 0. Okay, so this is our this is going to turn out to be our definition. So the definition is that a function f with domain D has an absolute maximum value, let's say f of c at x equals c, if f of x is less than or equal to f of c for every value of x in the domain. Okay, so let's take a look at this picture that illustrates this definition. So here's a domain for this function. Let's say the interval from a to b, and we'll just go like this here. So here's the graph. So this is our domain, and this is the function f of x, y equals f of x, the graph of the function y equals f of x. And right here, let's make this point c. So here the coordinates are c, f of c. And let's see why this is an absolute maximum. So we call this an absolute maximum if f of x is less than f of c for every value of x in the domain. So here, certainly that's true. No matter what x value you pick in between a and b, f of c will be at least as high as that value. So this is an absolute maximum value. Absolute minimum is exactly the same, works on exactly the same principle. So absolute min at f of c, absolute min f of c means f of c is less than or equal to f of x for all x in the domain. So we could draw a similar picture here. In our last example, we had x, the graph of y equals x squared. This was an absolute min. Okay, so this is the notion of an absolute value, or an absolute maximum or minimum. We call local max and min is when the phenomenon happens locally. So we've seen that example already. So let's go through an example. So here's a function x cubed, the x cubed function. Its graph looks like this. So here's a function that appears to have no absolute max, no absolute min, no local max, no local min. This function has no absolute max or min, no local max or min. It has a point where it almost looks like it wants to have a local maximum or local minimum, but it doesn't here. In fact, this point right here on the graph has points that are lower than it right nearby and points that are higher than it right nearby. So this has absolutely nothing. All right, let's state a theorem. This is the extreme, it's called the extreme value theorem. I don't know who named this. It always makes me think of the extreme value menu at Taco Bell. Anyway, here's the extreme value theorem. It says that if f of x is continuous, on a closed interval, continuous on a closed interval, then f achieves its absolute max and absolute min. On the interval. So let's just draw a few pictures of this to convince ourselves that this theorem is true. Okay. Remember what continuous function means. It means all you have to do is draw it without without lifting your pencil from the paper. Okay, there's an example of a continuous function on an interval. Here's an example of a continuous function. Here's an example of a continuous function. Okay. All of these examples here that we've drawn, they achieve their this function achieves its maximum and minimum value. So here's the, here are the candidates for these points. Here's a candidate, here are the candidates for these points. Okay. What do you observe about the points that I've circled? They're either the end points, so the candidates for absolute max and min values. One, they're either the end points of the interval. Here, this endpoint right here looks like the lowest point on the graph. So either endpoints, of the interval from A to B, or what do we see? We see these points right here. This one looks like the highest point for this graph. This one looks like the highest point for this graph. And this looks like the highest point for this graph. So these are places where there's a horizontal tangent line. Okay. And what do we know about horizontal tangent lines? That means that the derivative is equal to 0 at those points. Or a point like this, here's a sharp corner. This is a point, so a corner. This is a place where the derivative does not exist. Okay. So if we're looking on a closed interval and we have a continuous function, the candidates for the absolute maximum and minimum of heights of these functions are either endpoint values, places where the tangent line is horizontal, or places where the derivative doesn't exist. So places where the derivative is either equal to 0 or where the derivative does not exist. Okay. So so this is these two points are types of points are very important. We call these critical numbers. So critical numbers. So critical numbers are numbers where f prime equals 0 or f prime does not exist. Okay. So let's talk about the closed interval theorem. So we've established the following observation. If f of x has a local max or min at C, then C is a critical number. That means f prime of C equals 0 or f prime of C does not exist. Okay, this is just our observation. So now, this is also a result that's due to the mathematician Fermat, but I'd rather just use it as an observation. in terms of the following, what's called the closed interval method. The closed interval method for finding absolute max min values. Okay, so here's the method. So the question is to find the absolute max and min values for a continuous function on the interval from a to b. We would do the following. Okay, so step one is we find all critical numbers for f of x in AB. Okay, so that's the most important one. Find the values of f at a, b, and all the critical numbers. Okay. 3, the largest and smallest values from part 2 are the absolute max and min. Okay. These steps right here will be of fundamental importance to what we're going to do, all of the questions we're going to ask from section 3.1. So remember, the goal of this is to just find the highest and lowest values for a continuous function on a closed interval. And this is the process we go through. We find all of the critical numbers, so these would be the places where we suspect there could be an absolute maximum or an absolute minimum. And then we find all of the values at both the endpoints of the interval and at these critical numbers, and then we just look at those. So let's take an example where we employ this method here. So example, how about f of x is equal to x cubed minus 3x squared plus 1. And we'll look at the interval from minus a half to 4. Okay. So these are all the values, x bigger than or equal to minus a half and less than or equal to 4. So this is our a, and this is our b. This is the interval. Okay, find all max and min values. Okay, so let's do this using the closed interval method. So the first step that we had was to locate all of the critical numbers for this function. So we compute the derivative of this, and we get 3x squared minus 6x. Okay, that's the derivative. Okay, now we want to know all values. So the critical numbers are all values where f of x equals 0, or f prime of x does not exist. So we look for where the derivative is equal to 0 or the derivative doesn't exist. Okay, this one right here does not exist. This is a polynomial. There are no such x values. And the reason is because 3x squared minus 6x is a polynomial. So this is So that means that, so this is defined at every x value. So there's not going to be a number you could plug in here that makes this derivative not exist, because this is a polynomial. Okay, so there, so we don't have to worry about that. Here's the one where we do have to worry a little bit. So we set this equal to 0. Okay. A little bit of algebra here. I see a common 3 and a common x. If we factor 3x out of this equation here, we get x minus 2 is equal to 0. I think that's right, if my algebra is correct. So that means that, that x is either equal to 0 or x is equal to 2. Okay. So these are our critical numbers. Critical numbers for the function. Now we observe, okay, 0 and 2 both lie in this interval from minus a half to 4. So we really do have 4 numbers to check. So we check f of minus a half, f of 0, f of 2, and f of 4. Okay. So let's just see what these numbers come out to be. Okay. If we compute minus a half, I think we'll get 1/8. If we plug in 0 into f, we will get 1. If we plug in 2 into f, we will get minus 3. And if we plug 4 into f, we'll get 17. Okay. So we check. Okay. So now take a look. Which of these is the smallest and which is the largest? Okay. There's the smallest. So this is the min. And here's the largest. So this is the max. I don't know if you can see that or not. I just want to emphasize max, min. Okay. So if we draw a graph of this function, it would look something like this. I mean, we haven't drawn the graph, but if we were to draw the graph of this function, so here's minus a half, here's 4. The graph of this function looks something like this. Something like that. And so we would see that right here at 2 we have this local minimum. Right here at 0 we have this local maximum. That's a value of height of value of 1/8. And so down here this is our min, and up here the endpoint, this is our max value. Okay, so that's an example there. We'll go through tons and tons of examples of these when we work in class.